Starting with a cough. Hello. I see the transformation, the alchemy of Aminata in space.
Hello.
Hello. Oh, and even oh my God, it's so wild how that works. Okay. Hello with the double in space. Okay, and hello, Victoria, and hello, Kian, and hello, Vicky. And I'm going to the chat now. No, I love that. The whole avatar. It's so, what's great about the animated avatar is that it's so thrilling for me to watch and yet so easy for you guys to walk. I mean, I get that it totally covers you, but it covers you in a way that like I don't even care because I mean I care. Anyway, whatever. All right. Let's go. People are coming in. So good afternoon, Raina. Hello, Melanie. Good afternoon, Victoria with the double. Good afternoon, Vicky. Where's Vicky's animated avatar? It's not the same. Oh, there. A real person. Oh my God, she's got an animated avatar that's in 3 dimensions. All right, I gotta calm down. But for 2 semesters, that's what she looks like. You see what this? Okay, awesome. Okay, I'll shut up. But good to see you. Okay. Wait. All y'all, well, some of you are starting to know where my office is. I'm only there on Tuesdays, which stinks. I'll be there a lot more next semester. It doesn't help you. But you should come by on Tuesdays, any of you, because it's like 3 dimensions is so nice. Okay, so Melanie, yes, Victoria, yes, Vicky, yes. Oh, Bridget with the animation. Good afternoon, Caitlin with the double exclamation point. If you can do a good double explanation point 2 days before an exam, you're a good person. Good afternoon, Lachman. You're all good people. Good afternoon, Joel, with the double and with the early. Good afternoon, Kian with the double. Good afternoon, Mafine with Mafine. So, yeah, I remember there was an email. Oh yeah, and hello, Anthony. Okay, with the something. Okay. Hello. Okay, so we're all here. Back to the exam. I want to try to. My ideal today is to write things down. Well, okay, no, let's start with. Let me start with. We're going to do questions first, but I'm also going to say, again, this is one of those situations where I recommend that when we're all done with whatever this. Hopefully, we're just trying to help each other with this exam today. The exam that'll be posted Friday. And again, you haven't had lab yet, I don't think. Remember, in your lab session, even if all you do, tell me if I don't think you've had it yet. Tell me if I'm wrong, but I think you're going to have it tomorrow, right? In your lab session, if all you do is literally sit there and work on the practice exam as individuals and then work on the practice exam in groups, like even if Mercedes never gives you an answer, which is distinctly possible, even if she never says anything, and all you do is work for 3 hours on the document, I'm promising you right now that is super productive time well spent. And I'm telling you right now, again, just to reinforce, you should consider that time that you're working on rough drafts of your actual exam. Like by the time your exam is posted, yes, there will be differences, but there will be enough similarities that anything that you sit there and write out during your lab period tomorrow is like a rough draft for it. And I really think with an exam like this, you want to have done a rough draft and a final copy. It is about presentation in a like that does matter, like how you present things. So that's just a way of saying in advance that the purpose, unless you've already had tomorrow. Thank you, Aminata. Okay, so I'm just like trying to manage your expectations too. That like the purpose of the lab session is not that she's going to stand there and she's not doing a walkthrough. It's just giving you huge amount of time to get yourself off the ground and be together, which is hard to arrange outside of campus, right? Right. So okay, so that's that. So now I'm here to answer questions. So of course, if you don't ask any question, I will walk through stuff, of my own judgment, and I won't try to trick you if you do. But it would be better, I think, for all of you, if we pause for a moment and you collect yourself and you look through the document, and the more specific a question you can ask, like in part C, part D, should I have a minus sign here? Or like, the more specific a question you can ask, then the more of them I can answer right now. And I will. I'm not going to hold back on information. Um, So I'm going to pause for a second and say, please put whatever questions you have in the private chat or the public chat. Okay. And I'm going to wait till I get a bunch, even if I can't answer them all this period. I mean, if too many of them are like, can you walk through all of problem four? Like I might, but then I can't do anything else, right? So I'm going to look at all the questions right now, even if I don't, even if I triage and I do like the shorter questions first, and I don't get to all the long questions or whatever, I will also say it's good for you to know that I know what your concerns are before Friday. Because frankly, that's the other point of you going into the lab Thursday. Mercedes is like really good about the following. She's like really vigilant about always wanting to give me feedback on how you guys were feeling the day before an exam. Like sometimes I don't care. I mean, I care, but sometimes I forget to do like, but she will call me. There's going to be like, oh my God, they're totally freaking about problem three or whatever. And I won't like change the universe around that, but it will be good for me that to be in my consciousness, when I post the thing. So again, for today, put whatever questions or concerns you have, even if I can't answer them all, it's good for me to know them and good for you to know that I know them. Okay. So I'm going to shut up. I'm going to give you a couple minutes to put whatever questions in the private or the public chat. Okay. And then I'm going to like try to answer them. Oh, and this is one of those times where since it's like going to be organic, it's going to be like what you tell me to do. I highly recommend, I'll try to remember to post both videos. You should watch the video from the other class as well when you're preparing for this exam or doing this exam, because I'm sure different things will happen in the other section, the other recorded section of this class, right? You should watch them both because whatever. In fact, I'm going to try to make them very different so I can cover as much ground as possible. Okay, so I'm going to shut up for a moment. I'm going to ask you leaf through the things, see what you're concerned about. Try to come up with specific questions and put them in the chat, and then I will try to answer them. And in the mean, and I'm not going anywhere, but I'm going to fix something while you do that. Okay. Okay. Well, uh, yeah, all right. There is a question that, well, actually, I want to wait. There's at least one question that I will answer it, but I'd like to get a lot. I want to get a few more questions before I say anything. So please, I mean, again, this is your uh opportunity. Um, so I don't want to steamroll anybody. Um, well, all right, okay. I'm not keep them. I mean, there's only I'm. You should ask questions today. Today's the opportunity. And again, like you're allowed to ask any questions you want of Mercedes to of Professor Tally tomorrow, but you're allowed, as far as I'm concerned, as far as she's. But that doesn't mean she's going to answer them. Like it just may not be the way she structures the the day. So I would encourage you to err on the side of asking questions today, but I'm going to move on because there doesn't seem to be. There's one question I'm going to answer it, but you could keep at. Oh, here's okay. Here's another question. Okay, okay. Oh, okay. That's a good question. Okay, okay. There's two questions. Again, you can keep them coming. I'm not cutting off the opportunity, but I'm going to start getting rolling. And once I start talking, it gets sort of harder um, to get a word in edgewise. So there's two questions in the chat right now. Okay, one question is very fair, worth reading out. I mean, they're both fair, but oh, wait, there's three. Okay. Oh, that's a good question too. Whoa, interest. Oh my God. Sorry. It literally, I just did that weird falsetto thing or whatever singing thing, and then literally Zoom just like gave me an advertisement for setting up like FL Studio or something in this. That's really weird. Okay, okay. Oh, okay. Now there's a bunch of questions. Okay, 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 okay. In order. There's all good questions. One is a general thing. One, someone is asking me, can I give feedback on your work? Can I give on this work, on the exam work? Can I give feedback? Presumably meaning like, can I give feedback while you're working on it, or can I give feedback on your rough draft? I mean, on your practice exam. Like, I'm actually not sure which one they're asking, but it's a very fair request. But here's the answer is no. Well, the answer is no in this sense. Certainly, once the exam begins, the one thing I cannot do is give you feedback while you're working on the exam. You can ask other people. You can ask each other. You can ask your older sister, who has a PhD in physics or would like whatever. Like you can consult whoever, but you can't consult me. And part of the reason is there's like literally I don't have the time to do it for all of you. So I can't just help. I can't while the exam is going. I can't tell you if you're on the right track or not while the exam is going. I mean, because it is an exam, okay? And I literally just no, I just can't even though it's a fair question. Now, as far as the practice, there's not a lot again there too. I mean, as you see, sadly, I'm already like very behind on like normal feedback to you, like on homeworks and stuff like that. So just on the time management thing, I can't make a promise that I could sit down with your. There's no way with all of your practice midterms I could sit down and give them back to you in time for you to take this exam. That I just can't do it. But that's also partly why you're going to all help each other tomorrow and in the lab. But what I can do, I mean, this is part of what we have now. If you, the person who's asking for feedback, if you have a little chunk of something that you've been working on and you want to know whether like that's right or wrong, first of all, if it's like minor, if it's on the practice midterm to any of you, if it's concrete and concise, like, can you look at my part A of problem 3 and tell me if I'm on the right track? Yes, you can text me or email me that. I mean, again, make it super concrete. Realize that there's like 80 other students or something, so I can only do so much in 2 days. But yes, if you have something concrete and specific, you can text me or email me and say, "Is this basically what you're looking for here within reason?" Or whatever. And yes, I will respond to that. Again, why I like text is because if you could force it to be a text worthy thing rather than an email, then you're going to help us both. So okay, so I guess my answer to that is yes, if it's on the practice. Once Friday comes, no, but also you could put it in the screen right now. I'm not trying to put you under, but if you've got something and you want to like share it right now, that might be useful for everybody. And I would do it if it's concrete and specific. But if not right now, yes, to all of you, if you have a concrete specific thing that you want to text me, like think of yourself trying to answer a text. You want to do it fast and you want to do it simply. If you can make it simple for me, yes, I will say you're on the right track, or no, dude, where's your 5-step method, or like whatever. Okay, so that's my answer to that. Now, oh, right, that's my answer to that. Now, then then there's a question about the Doppler effect. I do plan to say more about the Doppler effect today. Like again, if there were no other questions, I would say more about the Doppler effect today. I will. But I will also admit, to be just totally honest, with the Doppler effect, like there's 4 cases that you have to do, and there's a big conclusion you have to come to at the end. Here's what I honestly feel is that I have walked you through like 2 of the cases. So as far as how to begin the Doppler effect, I highly request and suggest that you go back and that you play the videos from this semester, but you can also play past it. Like there's a video called, well, first there's a video from this semester, from your class, called Doppler Setup, or Doppler Background, or something like that. That's like the first video that if you're really confused on the Doppler effect, or you missed the class, or you're just like, wait, what? Which is fair. I mean, first there's a video called Doppler Background, or Background to Doppler, which like gives you the overview. Then the very next day, there's a video called Doppler Case Solved. Please watch, and there's a PDF, that I uploaded that same day. I think it's class like 14 or something.
Professor.
13, did you just say 13? Wow. Is that what you
No,
just?
no, Professor. I was gonna ask. It's posted in Google Classroom, right?
Oh, yeah. So all of this stuff. Okay. Yes. The answer is yes. But okay. So the person who's asking about the Doppler effect or any topic like that, like I'm just trying to be as efficient with all of you as possible. So if you're like, for whatever reason, I don't even know how to begin this, then yes, there's 2 videos about Doppler effect. One that tells you how to begin, and then one that solves the case for you. And yes, this is all in Google Classroom. Like whenever I talk about a video, they're all under. It's like one of the first. I might switch screens in a second if it helps people. But yes, every single class there's a video for it posted under classes or something, YouTube classes. Okay, and you can find it. And then for whatever that day is, if it's called class 14, then you go under class notes, and when it says class notes 14, that will be the PDF that goes with that. So definitely, and it's not too late like some people have been dealing with this the whole time, but if you're figuring this out now, that's fine. But do that. But then notice once you go to the YouTube channel, once you click the link to the YouTube channel for that class, you'll see all these playlists from all these past semesters of all this stuff. And I never say the same thing exactly the same way twice. So definitely, if you're trying to understand the Doppler effect, then do a search and find the Doppler effect from the past classes as well. Okay, that's in terms of getting started. If you're confused, and I agree that the problem is not written well, and I want to write it better for your exam. It doesn't. It's very. But just watch the old videos and look at the PDFs, and you'll see how to start it. But then to the rest of you, like I believe, yes, that we've already created the material for how you start it, how you solve a case, how you solve a second case. Like that's all in there in the videos. But then, yes, what you're being asked to do is make a comparison among the 4 cases at the end. And even that, there's definitely past videos on, but I don't know if I've been so explicit about it with you in the last couple of weeks. So in a couple of minutes, after I look at all the questions, I will attempt to say even more about what I'm looking for sort of the end of that problem. But yes, it won't make any sense until you understand the beginning of the problem. So I hope what I just said is helpful, but so I'm going to move on in a second, but I'm also trying to send a message to all of you. Like, this is like, layered. Like, I know in my heart, you know in your heart, I've been the person, I've been both people, okay? I've been the person that rocks a class and that always feels on top of it, whatever. And I've been the person that is totally struggling. I have been the person who, like, or for whatever reason, has other life going on and just like doesn't even check into the class until absolutely necessary. I've been that person. There are some of you, maybe, who are sort of just now because there's a midterm, like trying to figure out how this class works and that stuff. There's no shame in that, but like you got to do it, obviously, right? So what I'm saying is to those of you, any of you, if there's any of you who are just now like, oh my God, I don't even know how this class works. Like I haven't been doing anything for a month. I am telling you it's not too late. I am telling you that. Like maybe you're going to have to sweat more bullets than somebody else or something, but like the class is like, and talk to your friends because their ability to get an A will not be threatened if they pull you up to a B, like whoever you are. I'm serious. It is not too late to figure out that for everything that you don't understand, there is a video, there is a PDF, like, and there is time to figure it out still, legitimately. Please know that. It's designed to be that way. If there's one, whatever, I'll leave it at that. But it's not too late to like do something. But okay. Oh, okay, cool. I'm glad. Okay, cool. I mean it. Um, okay, now other questions. So and you can remind me, I'm watching the clock. I will try to get back to the Doppler effect like punchline by the end of this class. At worst, if I don't, I'll do it in the other section, but you can remind me. Like I do still want to say more about the Doppler effect. Okay. But wait, I'm looking at my, oh, good. No, I'm glad. I almost want to say more, but no, those of you, if no, I mean it. I mean, uh, I don't want to rabbit hole. I know, and I know everybody is here for a different reason at any given moment. Some people are here to get the nuance. Some people are here to get off the ground. I know that. And again, I've been all those people. I promise you. And whatever. What I'm trying to say, if I'm sure you've already noticed. Look, I'm not a dumb guy and you're not dumb people. Like many of you have IQs that are far higher than mine. Okay. It is not about IQ and it's not about ethics. It is about psychology. It's about your own relationship to yourself. Physics. I mean, well, I think everything is, but like I am telling you that the roadblocks to doing well in physics are roadblocks of self-confidence and self-love and all that. And not to be cheesy, but it's true. It's all about a battle against yourself. It's not a battle against me. And I know that because I've had the battle against myself for decades. Okay. And frequently I win. But I know the battle against self. And I'm here to tell you, I sympathize, I recognize that. And the way to unlock physics is to unlock your own personal bondage. I'm serious, whether study skills, test stress, all that kind of stuff. And one way to unlock the bondage is to believe me that I'm here rooting for you and that I know the worst thing that a person can believe is that it's too late and ever on anything. And the reason that's the worst thing for a person to believe is because it's not true. It's just not true. And if you ever come to my office, I'll sit you down and I'll share whatever about my own personal life to prove to you, like whatever, that I get it. But like, it's not, hey, look, it might be too late to get 100 on this exam, but you don't need to get 100 on this exam to do fine in the class. Okay, just leave it at that. It is not too late. And for all of those others of you that I'm talking who want to like rock the crap out of this or whatever, fine. It's also not too late for you guys to get the most glowing recommendation from me possible to graduate school, whatever it is you're looking for. The threshold is there and available to all of you. Okay. Yes, I mean it. And I mean it from personal experience. It's why I'm here. Anyway, okay. So the other questions. Um, oh yeah. So I guess I'll say this too. Wait. No, yeah. Oh, there's another question about the Doppler effect. Just another reminder. I'll get back to that. I will. Okay. Then there's a question about, I guess this is the last one. Okay, conservation, the max velocity question. Since that's where so sometimes can you explain more about how to use conservation of energy for the max velocity question? When I went to the Zoom MSRC meeting, they used a formula. I'm very curious what they used. That's interesting. I think I want to do that right now. It's 12:40. We have till 1:30 because that's kind of where we left off yesterday. And this seems to be the only other question that's not about the Doppler effect. So, so yes, so in other words, this person who's saying conservation of energy, max velocity question, she or he is talking about the pendulum that we were sort of in the middle of yesterday. So let me go right back to that right now. Um, yeah, let me go back to that. And if I start talking about it for too long, feel free in the chat to say, okay, can you please move on? Okay. Um, so I'm going to switch my screen. Bear with me for a second. Right. So this is problem 3. Uh, yeah. And I'm not doing all the 5-step method, everything. I'm just trying to give you whatever bullet points of physics knowledge I can today. You have to turn it into like a presentation. But um, so, so what was given, the key that was given, okay, this is the question that the person's talking about in the chat. And it's where we left off yesterday. It's like part 3 of problem 3 of this pendulum problem. Part 3 says, what's the maximum speed ever achieved by this particle? Now, what I did say yesterday that I'll stand by, and what you would write as like a step 3 GDP or something, and you would explain is is due to conservation of energy. Okay. And again, you would explain this more than I'm explaining it right now, but I'm just giving you the bullet point. Is it, I'm so scared that people are just going to copy this down. Okay, these are bullet points. Okay, due to conservation of energy, um, the max speed occurs at the bottom. Okay, so we're solving for the speed at the bottom. So that's the piece about conservation of energy that you would talk about. But then now, once you know that you're solving for the speed at the bottom, that's a key piece of information that I'm now going to use. Now, and I'm going to show you the solution now, the skeleton of it. But to actually do the solution, I don't recommend using conservation of energy. Like, let me be clear, and I think I was unclear about this Monday. Conservation of energy is what leads me to believe that the place that I'm solving for is the bottom. I mean, I like that has to be justified. The justification is conservation of energy. But now that I know that, I'm actually not going to use conservation of energy to solve for the speed. What am I going to do? I'm going to say, I'm going to say, I'm going to solve for V itself. How do I get V? how do we solve like for any V? This is how. We remember two things. Remember, number one, that that V, instantaneous velocity, is by definition derivative of position with respect to time, right? And by definition, an angle like now that would be good enough, except we don't know, we don't have an X function. We don't know anything about X. We don't, this is not a mass on a space. The dependent variable here is not X, it's theta, where the pendulum is in the arc. I don't know theta. I mean, I don't know X. I know theta. Is there a relationship between theta and X? Most certainly there is. The definition of theta is X over R, right? Like that's the definite arc length over radius. That's the definition of an angle measured in radians that we've been using since moment one of all of this radian stuff, right? So I know those two facts. Thus, and again, you explain them, but they're true. So, like, what is theta if we're given that d2 theta d2 equals over right? That, like, if we were given that differential equation, then what we know is that theta equals theta naught cosine pi over 8 times t, right? Now focus with me for a moment. Like, I believe I know that automatically from the given differential equation. But why do I know that? Because of all the huge explanation that we already went over when we practiced, which we did. I don't like on Monday. Like, I know that from the huge explanation and the step one, step two, step three that I gave in the very first part of this whole exam. The electrical current problem that we talked about Monday. So let me be clear again. If I did all that already in the document and I already showed, like I already took two derivatives and showed that when you have this differential equation, you have a cosine solution with an angular frequency that's the square root of the constant in the differential equation. Like, if I've already shown that, then I'm going to write right here, like, for explanation, see above, see problem one, part A. But maybe you're doing maybe there's choices in this exam, and this is the first time you're doing this. Like, I don't know. So then I would explain it all right here. I mean, right? Like, but I know at this point, like, so somewhere you got to explain, and you need to understand. But I believe it's true that this theta expression is a solution to that theta differential equation. Now, who cares? Well, I care because if that's an expression for theta as a function of time, if I multiply both sides by r, I get x as a function of time, right? So in other words, x equals r times that. Right now, again, this is a question in the chat. So, but I'm not looking at the chat, but I will in a second. So stop me for any of you, whether you ask this or not. Like, I am giving you the skeleton of the solution here, and I want you to. So if this is what they did in MSRC, but it just looked like a black magic formula, that hopefully it doesn't now. But I don't know what they did, but you should stop me if it doesn't make sense because we're almost there. This is an expression for x as a function of t. What I need is to differentiate that to get v as a function of t. So dx dt equals negative r theta times, like I'm doing chain rule, right? Just like we always do, sine of pi over 8t, right? This is, you see, okay, just like we've been doing, only now it might look more obscure because it has thetas in it instead of x's or something, and it has like pi's in it, but you don't care if you don't care, if you're solid with this. So that's an expression for dx dt. So that means that's an expression for v. So in order to get v max, all I need is to know what time I'm looking at to here. I'm gonna just write this on the next page. Sorry. So v V equals negative R theta. Sorry. Oh, and let me, and also, sorry, it's all looking very obscure here, but let's be clear also. What is R? R is the radius of a circle. R means the length of this pendulum string, which is given as 2 meters, right? So, I mean, this is, it may look all, we have almost all the information except for T. Like negative 2, and what's theta naught? It's given in the problem as pi over 12 radians. Right? So we have everything to plug in here. Other than the T. Also, let me say there's a negative sign. Is that weird? No. I mean, it might be weird, but it makes sense that there's a negative sign. Hold on, I'm going back to the screen. Oh, there's stuff in the chat. Okay, I'll look in a second. But there's a negative sign. Is that weird? No, I don't think that's weird because that original angle to the right in my picture or whatever, the original angle, the amplitude, I wrote as pi over 12, as in positive pi over 12. So anything that's like to the right apparently is positive. But of course, the thing is falling to the left, right? In other words, it is like an oscillator in that it's going to be moving in the opposite direction. I mean, it is an oscillator. What am I saying? So it's going to be moving in the opposite direction from where it is relative to the equilibrium. If it's on the right, it's moving to the left. If it's on the left, it's moving to the right. So it does make sense that there's a negative sign in this velocity expression, right? So the only thing left is for me to figure out what T to plug in, which I'll do, but let me just look in the chat just in case I made a mistake or something. Oh, did I? Oh, oh. Okay. So I see the chat. Thank you for telling me what they used in MSRC. I have a comment to make about that. Well, I wouldn't recommend. That's correct. I see what they're doing, and I could show you what they're doing. Wait, I'm just trying to figure out whether I should rabbit hole or not. The thing that what they did in the MSRC is correct, and they may have done it too quickly. I could break it down into steps for you, but here's the thing: their answer that they got in MSRC has a G in the answer. That's correct, but that's a little bit open-ended because we don't know what the value of G is yet at this point in the problem. Like it specifically tells you at the beginning, we're on a different, and it tells you for this reason, we're on a different planet. We don't know that G equals not, we don't know the value of G. So whatever they did in the FSRC, that's like fine. And if you understand it and you can explain it, it's fine. But you're going to get an answer that is based on G. To all of you, if that ever happens in an exam, like if you work and work and work, and then you get a final answer that still has some unknowns in it, don't like cry and throw out all of your work or walk away. If you have time, you might want to consider trying a different approach, but say you don't have time or whatever, then yes, leave your answer with a G in it and make a, for example, whatever the unknown is, and make a note and say this answer is in terms of G. This is a function of G. G remains as yet unknown, like we'll solve for it later or something. And you might not get full credit. Like I mean, that's not a completely correct answer, but you'll get most of the credit and you won't destroy all your work and all of that if it's correct. So that's what you do. But what I'm here to say, I'm doing a different approach so that I don't have that issue. Yeah, well, that's unfortunate. I mean, so I will, if we have time, I'll try to explain where that, I mean, that came from grab potential and kinetic energy. Like it's correct what they did. But yeah, it's incorrect reading of the problem to use the value of 9.8. That is incorrect. Like the problem says, don't do that. So this is a warning to everybody. I mean, I apologize on the behalf of the I mean, it's just a I don't, so yeah. Uh, so what do I do here? what do I do here? The only question is like, what's the time? Well, the good news is this is where the conservation of energy comes into play in my mind, because we said the time is the time taken to get to equilibrium, right? And so note above. So what is that? That's a quarter of a period, right? It literally is right, to get to equilibrium, right? Because a full period is all the way to the opposite side and back. So a half a period is all the way to the opposite side. So a quarter of a period is just halfway to equilibrium. So, and do we know the period? Yeah, because remember, we got the F equaled 1/12, I believe. You can look back, but I'm pretty sure we got the F equaled 1/12 hertz. So T equals 12 seconds. So, right? I mean, like the period, if you look back above, so T over 4 equals 3 seconds. So you plug that in, and that's how you get V. There's even other, I mean, you could even do it. There's other clever ways you could plug in for T without even using a number, which would be really impressive if you realize them while you're, I mean, you could plug it in terms of pi's, then the pi's cancel, but whatever. But that's how I would do that. Does that, hopefully that makes sense. Maybe the person who's asking me, maybe just tell me if that, I mean, I apologize about the confusion. Yes. Okay, great, great, great. Okay. So that's that. I'm looking at the time. Bear with me for a second, because is there more I wanted to say about that problem? Okay. If there aren't, what I'm going to do, we still have 33 minutes. That is enough time, I believe, I'm going to say a little bit more about this problem, and then I'll shift gears to the Doppler effect, okay? And I'll probably say nothing about problem 4 in this class, but I'll probably try to emphasize problem 4 in the other video, in the next class today, okay? But so I'm going to try to focus on finishing this and saying some things about the Doppler effect, but still keep the questions coming if they occur to you. So I'm going to go on. Well, 4, similar thing. I leave it to you to do section 4 of this problem, because it really, what you need to know for section 4 is, where does the maximum acceleration occur? Well, that's going to occur at an amplitude position, right? Maximum potential energy, minimum kinetic energy is at the amplitude. I mean, it's like Hooke's law, like where is the spring pulling the most when the spring is the most stretched, right? So maximum acceleration will occur at one of the amplitude points. And how do you solve for acceleration as a function of time? You take one more derivative of velocity. Like you just do the same thing we just did, but take another derivative. Okay, so I'll leave that to you. But now 5 is a little bit more involved. So problem 3, part 5. The point of part 5 is that now, I mean, this is like lab 2 in a way. We're now circling back and saying, okay, we've been treating a pendulum as though it acts mathematically like a mass on a spring. But I mean, and it seems intuitive. I mean, it's going back and forth and back and forth. Like a spring mass goes back and forth, back and forth. I mean, and it conserves energy so it seems intuitive that this sort of is like this, but do we know mathematically precise? Is it really fair for us to be saying that the exact same differential equation actually applies to a small angle pendulum the way the differential equation applies to a small displacement spring? Well, in question three, in part five, they're actually asking you to back up and do the physics, the mechanics physics, like the physics 203 physics, to actually justify why we believe that this differential equation applies to a pendulum, and then specifically why we believe that like all harmonic oscillators, it's not only described by this differential equation, but that the constant in the differential equation is just a bunch of material properties, i.e. parameters, so that the angular frequency is just the square root, like all the things that we've been doing, all the math for this whole exam. It's trying to say now, how do we actually know that that's actually true of a small angle pendulum? So it's asking you to prove it. So it's kind of asking you to do old physics 203 stuff, but sort of not easy physics 203 stuff in order to do this. So I'm going to quickly walk you through this right now. Again, thumbnail sketch of the high points that you need, but this is what I'm looking for. First of all, okay, so we're going to try to derive the diffie-q for small angle planar pendulum. That's what it's asking us to do here. And planar, like lab two, it means it's staying in a plane. It's not like going in a cone or something. And we are assuming that it's small angles. Like honestly, this won't even work if the angle gets too big. It won't work physically. It won't work mathematically if the angle's too big. Just like with a spring, I think somebody asked this like a month ago. With a spring, it won't work if you ask the spring to stretch too much in comparison to how long the spring is. So this is like not new that we have to restrict ourselves to reasonable, ranges of values. But therefore, before I even get going, let me remind you, when we're saying it's small angle, that actually can be phrased that opens up a math realization that we need for this argument, and that is on the equation sheet. Whoops, sorry. You can't see the thing. But if you look at the equation sheet of the document, the third equation in the left column is the small angle approximation. I mean, it says, and it's true in life in general, it's like a step 3 GDP. It says as angles get smaller and smaller, as they get closer and closer to zero, the ratio of the sine of the angle to the angle itself gets closer and closer to 1. In English, that means as the angle gets smaller and smaller, if you just multiply both sides by theta, it means that as long as you're measuring in radians, if you're measuring in radians, as angles get smaller and smaller, the value of the angle becomes harder and harder to distinguish from the sine itself. If you type, and now you want to maybe explain this before, or like note that you understand it, but like before I'm saying it, even before I do anything, like if I type 0.005 into my calculator, if my calculator's in radian mode, and I type 0.005 into the calculator, and then I hit sine, I'm going to get a number that's like 0.0049, like a number that's like super close to 0.005. And better yet, if I then type an even smaller number, like 0.00005, and hit sine, what it's going to spit back is a number that's even closer to that. Like as you get closer and closer to zero, the value of the angle and the value of the sine are like barely distinguishable. And if you think about the graph, of course, that makes sense. Like the sine graph starts off at 0, 0, and then goes up almost like in a diagonal line at first, almost like the function y equals x, right? And all the way to the limit, the sine of 0 is 0. So when you're around 0, the angle and the sine are really very close to the same value. That's called small angle approximation. Really important thing to know in the lab when you're dealing with pendulums. If they're at sufficiently small angles, like lower than 15 degrees, lower, in other words, than pi over 12, yeah, radians, like the angle and the sine are almost the same value. So I'm writing that down. Okay. So you need like know that. Then therefore what? Therefore, I go to the free body diagram. I'm going to do physics now, right? I'm looking at the time 105. Okay. Also, like I know the screen is all. Hold on, sorry. The original free body diagram. Sorry. Am I back? Okay. Uh, okay. The free body diagram. Sorry. The free body diagram. That's the picture of the pendulum. But the free body diagram is something like the pure free body diagram is something like this, right? And I'm not, those angles are not, I mean, those vectors are not meant to be equal. They are not equal. But that's the two forces acting on the pendulum. Now, I'm gonna, you want to think about this. I will be. This is another one of those things where I'm going to give you key lines to make this correct. But if you just copy my key lines, that's not what we're looking for. We're looking for you to understand and explain them. Obviously I keep saying that, but there's a reason I keep saying that. But in order to analyze, to do the physics here, we have a pure free body diagram. We're going to have to break it up into components, something into components, because the two forces are not parallel nor perpendicular to each other, right? So something has to be broken up. Okay. How physics students always ask, I mean, physicists are always like plagued by what do I break up into components? Well, the answer is to back up on the question. How you know which one to break up is you have to ask yourself, what coordinate system am I choosing? Like, what is my x-axis, y-axis, and z-axis, or whatever? Any components that don't lie along an axis is what needs to be broken up. We're breaking up vectors into components that lie along the pre-chosen coordinate axes of our system, and it's a choice. This is all Galileo's principle of relativity. So any choice is correct, but some choices will work a lot more conveniently and efficiently than others. So how do you know what choice to make for a coordinate system? One of the key lessons from Physics 203, whether you caught it or not, one of the key lessons is we always strategically, we choose our principal axis to line up with the direction of expected acceleration. You always strategically, it is best to place your principal axis along the line of known acceleration. Example, the inclined plane from Physics 203, right? When you do an inclined plane, what's really mystifying to people at first is that we break up gravity into mg sine theta and mg cos theta, right? Like that, right? Like mg is just like pointing down. And then you've got like normal force pointing up at an angle. What everybody does originally think, if they have time to think about it all, consciously, what we would all instinctively do is take the normal force because it looks like a hypotenuse, it looks like a diagonal line, and we would break that up into a horizontal and vertical like we've been used to with velocities and all that. And gravity looks fine. It's just pulling straight down. But instead, our lab instructors and everybody tells us or advises us to take gravity and break it into mg sine and mg cosine. Now, eventually, of course, everybody just like memorizes that and moves on with their lives. But please try to remember that that might have been jostling to you at first. And you might never have understood why we did that. The reason we did that is we were saying, look, we know the object is going to accelerate along a slant. So if we slant our coordinate system, if we line up the x-axis with the slant, we will have as few sines and cosines to deal with as possible. Like that's the strategy, is you line up the x-axis with the acceleration. So then once we did that, then gravity was off kilter. Gravity had a component along and a component. Okay, I'm just reminding you. So we do that always in physics. When something is in an arc, when something is traveling in the arc of a circle, the only way that it can possibly be curving, even if it's maintaining the same speed, even if it's a horizontal curve, a horizontal circle, the only way something curves is if it's continuously accelerating toward the center of that curve. It's called centripetal acceleration, you may recall. Honestly, you may or may not recall, but that is true. Like right? Because Newton's first law, Galileo's principle of relativity. If you're left to your own devices, you're just going to go straight, constant velocity, constant speed, constant direction. If you're curving, it's because you're being forced to curve. It's because something is knocking you continuously toward the center of a circle. You cannot curve without accelerating continuously toward the center of the curve. That is called centripetal acceleration, right? Even if you're not changing your speed, you must be changing your direction if you're curving. So whenever we're dealing with an arc, a curve, the axes that I always break everything up, I always then break up things into a centripetal axis, which points to the center of that curve, and then everything perpendicular to that, a centripetal axis, and then a tangential axis, and then a z-axis if there is one. There isn't one here, right? Like, so so you think about that. You think about that. No, think about that. Talk about what, and be able to explain to me, but I'm saying we're going to break apart into a centripetal and tangential axes, meaning tension is fine. It's totally along the centripetal, the radial line. It's gravity that is not fine. So I break up and I say tension and mg sine and mg cosine. Oh, sorry, because like the angle that I'm talking about is right here. So mg sine is opposite to that. That's another question. How did I know sine cosine? Think about that on your own, or you could text me. There's a million ways to do the geometry and see it, but it is just like a little inclined plane. I mean, at any given moment, the thing is on its own little inclined plane. It's just that the angle keeps changing, but the direction along the tangent line along the plane is sine. Now, I'm watching the clock. That's a component diagram. Now, I'm going to say this again. This is a pro tip. So F net equals MA. F net equals MA along each axis independently, right? F cent equals MA cent, while at the same time, but independently, F tan equals MA tan, right? Now, okay, so like along cent, so like, for example, in other words, okay, I'll just do this. T minus mg cosine theta equals MA cent. You may recall from physics 203, that means it equals mv squared over r. Now, I'm going to, oh, wait, sorry. Yeah, oh, yeah. Sorry, is it okay to label the vectors as f like sub t and f sub g? Why? I mean, wait, f sub t. Sure. I see what you're saying. Yeah, sure. Yeah. Sorry. Oh, yes. Um, but here's a pro tip for everybody. Here's something that's not okay. And again, it's just like the reward for paying attention today or whatever is like t minus mg cosine theta equals ma cent. Okay, that's one axis. And then I'm going to say on the other axis, here comes the negative mg sine theta equals ma tan. Now, first of all, where did I get that negative sign? Because again, the thing I was saying before, if theta is opening up positively to the right, then mg, what's pulling it down, is going to the left. It's like the opposite. So there's a negative sign, okay? But the pro tip is t minus mg cosine theta, those two vectors do not balance each other. People always say this, and I look for it. Do not believe that t and mg cosine theta balance each other. If they're equal and opposite, then there's no acceleration along that line, and then it doesn't curve. It's just going to fall straight down. The only way it curves is if if there's a net force and therefore an acceleration along that line. And that acceleration is called v squared over r. It's centric, so in other words, t minus mg cosine theta does not equal 0. It equals mv squared over r. But So don't say that they're equal to zero. That's the pro tip. But I also don't care about that axis. The axis I'm going to focus on, because this axis, the tangential axis, is where the motion is occurring. The displacement per time, the motion is occurring along the arc. So that's if I'm trying to see if this thing is actually acting like a mass on a spring, if I'm trying to find out whether the amount that I pull it back from equilibrium actually is determining the rate at which it accelerates toward equilibrium, then I'm going to look at where it is relative to equilibrium along that arc. I'm looking at its axis of motion. Okay, here's motion. So I'm the other axis. It's not balanced. It's just not relevant to my analysis. So I look at mg sine negative mg sine theta equals ma tangential acceleration, not so in other words the change in speed, not the change in direction, right? That's my statement. Again, I mean this is you got to explain stuff, but this is like what's correct. All right, so I could cancel out the m's from both sides. I'm almost done. Okay, cancel out the m's. But what's going on? Like okay, what is a tan? A tan mean acceleration, traditional acceleration, tangential acceleration, the rate at which you're changing your speed along the direction that you're actually going. In other words, what that is, and you can remind me of why you believe this, but it is calculus, right? Acceleration means the second derivative of position with respect to time. So I can substitute that in. So negative g sine theta equals d2 x dt squared. So we're getting somewhere. We're almost looking like a differential equation. Did I forget something? No, I didn't. Okay, right. We're almost somewhere. However, that's d2x. Like the definition of acceleration is second derivative of position with respect to time. That's position, that's x. But I want to be analyzing this whole thing in terms of theta, like the original differential equation treated theta as a dependent variable, as it should, because we're looking at something swinging back and forth in an arc. So I've got too many variables here, but we've already noted x equals L, sorry, whoa, hello, equals R theta, and in this case, R is L. So x equals L theta. So I could substitute in. So now I've got negative g sine theta equals d to L theta dt squared. And I could pull the constant out of the derivative, just like you can pull constants out of integrals. Right? Now we're really almost there. The only thing is we got theta on one side, we got sine of theta on the other. Like what? But small angle approximation. In small angles, right? See above, the thing we already, the GDP in small, well, right? We already said this, right? So I'm going to substitute, right? I'm just substituting theta for sine theta. Because small angle approximation. Now look, I'm just about to, now rearrange, divide both sides by L. Thus, so it's approximate, but that's also true of Hooke's law. It's approximate to the extent that you're talking about small displacements. Thus, d2 equals negative g over L theta. And look at that. So first of all, so that's what you're trying to do. And that's what you do. Just explain, explain, explain. But first of all, look, that's the differential equation that shows simple harmonic oscillation. right? And furthermore, if that's what we just wrote, if we just wrote, and yes, it's approximate. That's okay. It's approximate to the extent that the angle is small, just like springs are approximately true to the extent that the displacements are small. That don't get bogged down. Don't get freaked out by that. Um, but we got this. So like, right, like it's second time derivative of variable equals negative times some constant times the variable. That's simple harmonic oscillation. And like we said earlier, that means theta equals theta naught cosine of what? Of square root of GL times T. That's a mess, right? Like, in other words, the omega is the square root of whatever's the constant. This is like saying omega equals square root of K over M. We're saying for a pendulum, it's square root of G over L. It's actually beautiful, I think. So now, and I'm done with this, but that's how you do that. But therefore, you could go to the last part of the problem. Now, the whole reason you weren't told G, you could is because G is now figure outable from this. In fact, this is a way to figure out G, like on a planet. I mean, in a weird way, this is actually what Galileo did to figure out. But I just forgot where. Right. So now you can go to part 6, and you can get the value of G by saying if omega equals the square root of G over L, then G equals omega squared times L, and omega and L you have from above. Well, L is given, and omega you figured out in the first part of the problem. So that's how you do that problem. Okay. Now I have 8 minutes. I want to say more things about the Doppler effect. This is going to be a saying thing, not a writing thing. Yeah, I mean, again, to do the computations of the Doppler effect, I mean, I feel like I've given you I'm not trying to be weird, but I mean, I feel like you have the roadmap for doing each case of the Doppler effect. Like it's in the videos, it's in the PDF. And again, if the video, if you're just about to understand and I say it in a weird way, and you don't like, just like play a past video because I'll say it slightly differently of how to solve the cases. Again, if you use that equation that's on, I mean, the mechanism that I'm teaching you, that I'm testing you on, is that, okay, I'm going to try to, here, so I'm shifting gears. Doppler effect notes. One, the method the method of solving each case centers on wavelength. The whole point of the way I'm teaching you is that you look from the source perspective, solve for the wavelength, and you do that because the one thing that will always be agreed upon between the source and the receiver is the wavelength. The one thing that one and only thing that the receiver and the source will agree on in any individual case is the wavelength. So you go to the source, solve for the wavelength, then use that wavelength at the receiver to solve for the frequency. Like that's the method I'm saying every single time. But the key, like pro tip that I want to be as explicit as possible here is you're using the wavelength because within a case, the wavelength is what will be agreed on within each case. Like this, no matter what frame of reference you're in, you'll agree on the wavelength. The proper physics word for that is that wavelength is invariant, meaning no matter what perspective you're in, you're still going to get the same value. Invariant, like it's deeper than constant. It's invariant. But the thing I want to caution you when you're practicing this and stuff, um, wavelength won't be the same from case to case. Not only is that what confuses people, but that's actually the whole issue in the end of the day of the problem. We have 5 minutes. From case to case, the reason you're going to get 4 different answers for the Doppler effect, and I was saying this Monday, right? I would have expected to get 2 different answers. I would have expected to get one answer for an approach situation and one answer for a receipt situation, but I would have thought it doesn't matter whether the source is approaching or the receiver is approaching. I would have just thought if it's approach, uh, we'll get a certain answer. That turns out not to be true. You will get 4 different answers, right? And the reason is, and that wouldn't be true if you were throwing baseballs. And sometimes on this exam, I ask people to compare to what would happen if they were throwing baseballs. But because it's waves, not baseballs, you get 4 different answers, not 2. And here's why. I mean, I know yesterday I said it's because of the medium. And yes, that's what you're going to explain. It's because of the medium. But let me be more specific now in 4 minutes and tell you what I mean about the medium. Whenever when the receiver moves relative to the medium, the receiver receives a customary expected wavelength, but at an uncustomary, unexpected speed. Like literally, that's a fact. Like, right? If you're creating waves, you're yelling at me while I run toward you, the sounds you're producing are coming out of you at 340 meters per second, like relative to the air, relative to you, and a certain frequency, let's say 800 hertz, right? So they're going to come out of you at exactly whatever wavelength we would always expect them to come out of, like 340 divided by 800, whatever. And they're coming along at an expected wavelength, but I'm running toward them. So I get normal wavelengths, but I get them hitting, but I'm running into them. So I get them at an unexpected, unnormal, if you like, atypical speed. If the receiver is moving, then the receiver will receive customary wavelengths at an uncustomary speed. However, so in 2 of the cases, both the receiver moving, the wavelength you get will be like regular every day, just like 340 over the frequency. In the case of the homework problem, homework 4, I think that was 0.425 meters in 2 of the cases. But then if the source is moving, the whole thing is if the source is moving, then right from the get-go, when the source is moving, the source sends out a wave that's going at whatever speed it has to relative to the air, but the source is moving relative to the air. So right from the get-go, like if every second the sound goes 340 meters forward in the air, the source also moves forward relative to that air, say 80 meters. So the sound is only 260 meters ahead of the source right from the get-go in the air. So that affects the wavelength. I'm saying when the source moves relative to the medium, we get an unexpected wavelength. If the source is moving toward the receiver, it compresses the wavelength because it's like running toward the sound while it makes the sound. And the sound doesn't care what it's doing, it's just doing its thing in air. So if the source is coming toward, you get a shorter wavelength, like 0.325. And then that shorter wavelength comes to the receiver. The receiver thinks it's coming at a normal, not thinks, measures that it's coming in at a normal speed. Like the receiver's just sitting there in the air. The sound's coming along in the air at 340. The receiver's like, there's no problem. It's 340 meters per second. But what's coming toward the receiver is a shortened wavelength. So the receiver gets a different frequency. And if the source was running away, the receiver would get an extended wavelength. So in sum, with 1 minute left, I am saying, and you want to understand this, when the receiver moves, it gets a customary wavelength at an uncustomary speed. But when the source moves, we send an uncustomary wavelength at a customary speed. If you write that down, if you can follow that, you really understand. That's like the punchline of the whole Doppler effect thing. That's why the source numbers are that's why all cases get different numbers. And everything I just said would only happen with waves. It would not happen with particles because there's no medium for particles. So there'd be no compression or extension of wavelength or distance between particles. That's the deal. Feel free to text or email or whatever. And you can hang out for a second and ask questions if you for like a minute. But the recording is over and my alarm's going. Okay, so bye. I wish you all the best. Tie goes to the runner. Just work hard, have fun. Yes, and stay healthy. Yes, have a nice day.